Alrighty. A wedge of 11 kilograms is held on the ground with its base horizontal and smooth faces, so no friction. Thank God. Inclined at 30 degrees and 45 degrees respectively. The 5 kilogram mass is on the 30-degree angle connected to the 7 kilogram mass faced by the lightning associated path. Yeah. This one is released from rest and the wedge does not move. Find the acceleration of the particles and the force exerted on the ground. So we're going to do the up versus down equation as well. That's in play here. So what I'm thinking we do first is I move this over here and I'm going to make this diagram. I'm going to put this diagram down here as well in a minute. Now, let's begin with breaking up your gravity triangle for the 5 kilogram particle. Do stuff we can actually do. So that one there. So 2 gravity triangles in effect here. And actually I will put them directly underneath the particle so we can explain the R values as well. Alrighty. So that's going to be 30. Going to be 45. You're going to be, that's going to be 5G. This is going to be 5G cos 30, which we all should know is 5 root 3 over 2G. The other one is 5G sine 30, which should simply be 5 over 2G. Okay. This one here, lads. 45 degrees, so what we're looking at here, 7G straight down. And then 7G over root 2. And 7G over root 2 as well. Some of you probably have a slightly different version of that. What's 7 cos 45? Oh, just give it to you in third form. Oh, I'm in radians. Also, before your exam begins, make sure you're not in radians. You can use 7 root 2 over 2 as well if you want. I'd rather just have 7 over root 2 because there's less writing and less fractions. It's just the root 2's on the bottom, it's no big deal. Okay? Now, there's going to be a reaction force. I'll call this reaction force R. And that's R. And this one here is, anybody? Let's call it S. Is that alright? Now, I'm thinking we get away with treating it like a, I'm thinking we might get away with treating it like a, it's not a way you'd usually do the wedge triangle, wouldn't you? And what you'd usually say is that the wedge affects, the 5 kilogram, the 5, so imagine for argument's sake there's an acceleration A. Yeah? Usually the wedge will affect the 5 kilogram particle in the following manner. 30 degrees, that's A, and then this will be A cos 30, which is root 3 over 2A, and then downwards would be a half A. And we usually say that it's technically sinking into the ground, don't we? But because the wedge isn't moving one iota, what does that mean? Does any of that even matter? It doesn't matter at all, does it? Because it's not moving. Yes?
Can you just explain why that is the case there?
Why doesn't it? So what usually happens is we end up doing a formula. So there's 2 formulas, parallel to the plane and perpendicular to the plane. Okay? So if I was to do perpendicular to the plane now, here's what I'd normally do. What I'd normally do is I say force going upwards and downwards, okay? And what we'd say here is that if that's going to the right, pushing it, that means A is going to the right. So it means we'd look at this component here, Connor. See that component there? That's sinking into the ground. Okay? So we do force equals MA, and it'll be 5 times. Now, usually we'd say that we have this one has an acceleration B up the hill, and this one has an acceleration B down the hill. Okay? Relative to the movement of the wedge. And what we'd usually say is 5 times B. So in this case, I'm going to do perpendicular to the plane first. Perpendicular to the plane would mean that I'm going diagonally down. Because half A is the only acceleration that digs down into the face of the plane. So I'd do 5 times a half A, like so. And then I'd look at what components are in that direction. And the two components that are in that direction are R and 5 root 3 over 2G. The one going down beats the one going up. So therefore, actually, I'm sorry I'm going to use this anyway, Connor, so good thing that we're doing this. Okay? So, what happens here is I end up saying, no bother, it's 5 root 3 over 2. G, take away, R. Alright? But in this case, the A value equals 0. So this implies that R must be equal to 5 root 3 over 2 G. Okay? Now, what we'd also have to do, because there's two different slopes of the wedge, I'd have to do yet another gravity triangle, okay? Now, before I do that, I'm just going to finish up with this one here, okay? That's perpendicular to the plane. I also have to do a formula parallel to the plane. And because we've decided that 5 is going up the hill, we've decided 5 is going up the hill, haven't we? All right. What opposes its motion up the hill, or actually goes with its motion up the hill? I'll show you now. So we're deciding that B goes up the hill. That means that, notice that the root 3 over 2 was also going in that direction as well. That was also going in this direction as well, right? So it actually has a combined acceleration. In the same way, if you're on a moving train and the train is accelerating at 5 meters per second to the right, and you're on the train and you're accelerating at 2 meters per second to the right, you have a combined acceleration of 7 meters per second squared to the right to a stationary observer. Okay, that's what I'm basically saying. If the wedge was to move with your particle on it, it affects its acceleration. Okay? Now, next thing we're going to do is we're going to do parallel to the plane. Okay? So if we look at parallel to the plane, I'll try and do it up here, right? It's 5 kilograms multiplied by B. And in this case, you're adding them together, aren't you? So that's root 3 over 2 A, because it's going in the same direction. Okay? And what drives up the hill? T drives up the hill. And what opposes its motion up the hill? Which is 5 over 2 G for this particle. Right? Now, what do we know about A? Oh, no. Right. Oh, I have to take it down bit by bit. I hate doing that. All right. Would everyone agree that A is equal to 0? What's left over then? I'd say that 5B equals what? 5G over 2, right? And that's my second equation. So I've successfully got two equations from parallel and perpendicular of the 5 kilogram particle. So in a way, I am sort of officially officially done with this, okay? So let's get rid of that and get rid of this, okay? Now, I now move over to the other particle. And what angle is the other particle on? It's on what slope? 45 degrees, okay? And I create a triangle that has parallel and perpendicular to that slope. Don't let that throw you off there. Yeah, it is confusing. Now, just try and pay attention to this one, right? 45 degrees. Is that cool with you? Alrighty. Now, we've agreed that B is going. So we agreed that it has acceleration going down the hill, don't we? We all agreed it's going down the hill. Now, the best way to think of this is, imagine you got knocked over by, I don't know, do you know one of those ice scrapers they have in America, where they have it's like a shovel, but it's at a slant. Okay? What would happen if you got knocked over by it? What forces would you experience? Would you feel like you're sinking into it or you're getting thrown upwards? You'd feel like you're getting thrown upwards, wouldn't you? And that you're not sinking in. That'd be the first thing you're experiencing. Second thing is sometimes you sort of slide down it anyway, don't you? That makes sense? So imagine that somebody comes in behind you and sort of pushes you in your lower back. You feel like you're going to go upwards, right? So you're going to find that the mats will support this natural feeling, okay? So here's how the mat supports this natural feeling. So here's what we're looking at. The acceleration A is always the hypotenuse, okay? The acceleration of the wedge is always the hypotenuse, okay? In this case, that would be A over root 2, because it's A cos 45 and A sine 45. Using the triangle law, what direction does this have to go? Now, for those of you that don't remember the triangle law, if I want to walk from the start to the end, I can walk straight across like so, or I can go diagonal right up, followed by diagonal right down. That gives you the direction of the acceleration of each component. So this one is going diagonal right up, and this one's going diagonal right down. So get this. When you get hit over by that ice clearer or the snow plow, this component here is the part that you feel like you're getting thrown out. And this part here is the part where you feel like you're sliding down a bit faster than you would normally. The opposite is true. If you're at the back of a car, once again, I'm taking action movies here, right? You're at the back of a car at the window section, and the car is driving off. What you always see happen to the superhero? He just goes flying downwards, doesn't he? Because he feels like the car's been swept from under him, and that's why you have a sinking feeling that you're just going to hit the ground a lot faster, right? So when you're at the front of the car, you feel support, like you're getting pushed outwards. When you're at the back of the car falling off it, you feel like the ground is being swept from underneath you. And that's why the accelerations either work against you, driving you into the slope, or driving you out of the slope. So what I mean by that is, for this one, it felt like it was driving you into the slope, and for the 7 kilogram particle, it feels like it's driving you out of the slope. Right? That's how I remembered it. I was thinking Bruce Willis, Die Hard, and falling off stuff. That's how I remember this. Okay. So here's what we're going to do next. We are going to do parallel and perpendicular for the 7 kilogram particle. Okay. So let's have a look at the 7 kilogram particle. Let's start off with a perpendicular. What are the two forces that are perpendicular? Highlight them in green. What's that? The reaction force to the ground. And what's the other one? 7g over root 2. Is that right? So what are we going to say then? So what we're going to say is 7 times its acceleration. 7 times a over root 2. And what direction is a over root 2 going in? It's the car is knocking you over. You're at the front of the car. So it's diagonal right up. Okay? What force goes diagonally right up? S or 7g over root 2? S. You put S first, and then minus 7g root 2 second, and then what are you getting now? What do we know about the A value? What do we know about the S value then? And now we have both reaction forces here, don't we? Does that make sense? We have both reaction forces sorted. Okay. So that's that part of the question done. You will use that in part 2, not in part 1. Now, what's the next part we're going to do then? Parallel to the axis. All right. So what do you reckon parallel to the axis? B is going downhill. What else is going downhill? Yeah, so it's a combined acceleration. It's 7 times B plus A over root 2. And they're both going diagonally right down, aren't they? What's driving it diagonally right down? Highlight the two forces. So we'll highlight them in blue. 7g over root 2 and t. But is t pulling it diagonally left up or forcing it diagonally right down? Diagonally left up. So in this case, it will be. By the way, this is a very tough question, right? You might have even picked around it on the day. But what do we get? 7g root 2 forcing it downwards. Minus t. Here's the good news now, lads. Good news is A is 0. And what does this become? 7b equals 7g over root 2 minus t. Happy days. What am I going to do with those two equations? Add them together and cancel their t's. And I'm going to get 12b equals whatever 7g root 2 minus 5 over 2 is. I'll probably try and keep it in short form where possible. So it's going to be 7g, so 7 over root 2, take away 5 over 2. And what you get? That, I suppose, would be divided by 12 and turn it into a decimal. Might be in our best interest, would it? It doesn't say we have to keep it in third form, does it? No. Yeah, to hell with that. 0.20204. Are we okay with that? I'm also going to get the t value while I'm here. What's the t value? 5 times b plus 5 over 2 g. And then what do we say there then? Anybody? 5 times b plus 5 over 2 times g. So 5 times, yes, yeah. Sorry? Oh, I have to multiply by g, do I? Oh, sorry, my fault. I forgot the g at the end. So, sorry guys, it's 0.204 multiplied by 9.8. Thank you very much. That would have been costly. Pretty much 2 on the money, isn't it? Alright, so 2 meters per second on the money, but we'll take that. That's a nice number. So instead, 5 times 2 plus 5 over 2 times 9.8. Right, just tell me what you get when you throw that in. 34.5 newtons. They're nice numbers, aren't they? Now that I have all this information, guess what's going to happen? We've successfully done part A. That's great. And here's what I have to do next. I don't need any of this. I don't even need the acceleration. All what I need now is the forces. Because what does part 2 say? This is tricky in its own right. The vertical force it exerts on the ground. So, I go back to my original wedge. What is it? 30 degrees and that's around. All right, so here it is. go back to the original wedge, which is 30 degrees and 45 degrees. Everybody cool with that? How much does it weigh? The wedge. Huh? Question. Why don't we just add on 5 kg and 7 kg? Why don't we just say it's like 23 kilograms in total? Is it fully supporting the weight? No, because they're sliding and moving. If that was a rectangle and the 5 and 7 were sitting nice and cozy on top, could you just say it's 23 downwards? You could, alright? But that's not the case here. Now, we're going to ignore them and we're going to work off the forces, alright? Just one thing, we're going to start off with the most awkward part, the tensions. Imagine as an example, once again, stupid action movie. In this case, Bruce Willis lassos a rope over somebody else's head to support some person who's dying, okay? Or about to fall off a cliff. What does the person who has his head lassoed feel? And let's talk about pain and force. What type of force does he feel? I think he feels force acting downwards, doesn't he? Along the rope. So the same is true for the wedge. It feels a tension force acting along its two edges like so. Once again, equate what you would feel to the wedge and you come up with a rough idea of what way the forces should go. Okay? Refer back to Bruce Willis, right? Now, or whatever your modern day Bruce Willis is. Alright guys, 30 degrees. So what can I say about this tension force up here? The blue one. What are we going to say about the blue one? What you reckon? So tension going this way. 30 degrees Y. Alternate angles. Okay, so it's 30 degrees. This one's 30. The other one's 60. We wanted it that way. And all I need to be worried about is the downward force. I don't need to worry about the force going left and right. So I'm going to go for T sine 30. Is that right? Which is a half T going downwards. Everybody cool with that? And actually, I know what a half T is, don't I? I can put that in later. Now, what we're going to say about this one here, the yellow one. The yellow here. What are we going to say about him? Got to break it up all individually. So what are we going to say about this one? What angle this time? Yeah. So T on the diagonal, 45 here, and we're just going to say T over root 2 going downwards. Okay? We've resolved the tension into downward forces. We don't have to be worried about the left and the right because we know it doesn't move. So that's inconsequential to me. Next thing, what we're going to do is we are going to solve out the R's now, right? So I have to leave this here for marks. Yes? If it was moving, they'd more than likely be asking me about the acceleration of the wedge. And I'd have to do like a general formula that the acceleration of the wedge would be 11, let's for argument's sake call it 11A, going to the right. And I'd have to do all the forces going to the right minus all the forces going to the left. So this tension would be going to the left, while the other tension would actually be going to the right, and I'd resolve it that way. Okay, but I don't have to do that here, so I'm not going to bother. Now, next thing is what reaction force do we have here? It's R, isn't it? Everybody see R? R is going diagonally left, up. Likewise, when Bruce Willis headers a football in the World Cup final, you feel a reaction force. When you header a ball, the ball feels a force going upwards, but you feel the ball putting pressure on your head going downwards. Okay? I've decided everything's been taught through Bruce Willis, alright? And so this is R here. Everybody cool with that? Everybody happy that's R? Now what are the two angles in question, so? What do we reckon? That's 60, isn't it? and that would be 30. So what do we have for R? I just want the downward one. I'm not even bothered with the upward one. What's the downward one? R cos 30, which is root 3 over 2. R. Right, this is awful. Right? The next one. S. Same thing. Header in a football. S is now acting. You see why you absolutely need a huge diagram for this. That's S going there, isn't it? Once again, what do we need to do? Resolve it parallel and perpendicular. So S in this case will be, S is going to the left, while R will be going to the right. And that's going to be an angle of 45, no matter what way we slice it up. So it's going to be S over root 2. Finally, I'm going to add all my downward forces. Yes?
I don't really understand why is awareness going
Into the wedge.
Okay.
So basically, anytime you support a weight on your head, Connor, you put like a stack of books on your head. The books feel like you're supporting them upwards. But from your perspective, you feel the reaction of the books forcing you downwards. So the wedge, while it supports the particles going vertically upwards, like so, from the wedge's perspective, it feels the weight pushing it downwards. It's the whole reason why wedges move in the first place. If we have a right angle triangle like so, and I put a weight here, the wedge moves. That's because the reaction force of the block is forcing diagonally right down, which has both a downward component and a component going straight to the right. And that's what forces its acceleration to the right. Okay? What? Yeah, it's not fully supporting the block. So the block is sliding, but nonetheless, it's still pushing the wedge to the right. Try when you go home sometimes. Just grab this, put a weight on it, and fit and experience what you feel. If this is a wedge, it will get forced to the right as the thing goes down. Every time. Unless the friction on the ground is exceptionally strong. All right, guys. Now here's what we're left with now. We're left with the forces all acting downwards. We're going to go for good old-fashioned pink. 1, 2, 3, 4, 5. 5 different parts. Ready for this? Okay, so we have a half t plus t over root 2. We have root 3 over 2r. This is awful. And we also have s over root 2. And we also have 11g. Why is it 11g? Because it's the actual force. So the overall force is a half t plus t over root 2 plus s over root 2. I forgot one of the s's, didn't I? No, I didn't forget one of the s's. Balanced with the r. Plus 11g. Now, somebody's going to be so nice as to put all this in the calculator for me. All over root 2. Did we get s? We would just put these in decimals. S and r. Somebody be so nice as to get s and r to about 3 decimal places for me. I don't fancy putting all those thirds in. Oh, yeah, awesome, actually, yeah, good points. The root 2's will cancel, won't they? Oh, sorry, they won't cancel. S over root 2 will be 7g over 2, is it? Because the root 2 is multiplied by 2, so it'll be 7g over 2, and r over The root 3r makes that easy as well, because then root 3r is, sorry, root 3 over 2r will be 15 over 4g. Is that right? So 7 over 2 times g and 15 over 4 times g. So 7 over 2 times g and plus 15 over 4 times g plus 11 times g. And what do you get when you throw all that in? Hopefully the correct answer. Many people definitely think I got it wrong at this stage. I do. All right, what do we get? Technique was perfect, but whether we made an error or not is a different matter. I'm not lying. If you see that in your leaving cert, pick around it. You do not want to enter that. So what you get? Newtons. All right.